Hi, this lesson is about logarithmic functions. So every exponential function of the form y equal to b to the x can be rewritten as a logarithmic function and vice versa. So if y equals b to the x, that is rewritten as x equals log base b of y, where the exponent is now the value on the other side of the logarithm. The base of the logarithm is the same base as in your exponential, and the expression on the other side of the exponential, in this case the y, that's what you're taking the log of. So again, some of the vocabulary that we need to remember is that in an exponential, b is the base and x is the exponent. Remember, the base has to be greater than 0, and the exponent can be any real number. So we read this expression as log base b of y, and it has the same restrictions for base. And here's just other notation. It doesn't have to be called b. Here it's called a. It really could be called anything you want to call it, as long as your b is a positive number. You have your exponential function that can get rewritten as a logarithmic and vice versa. So to convert from exponential form to logarithmic form, the coefficient of b to the x must be 1. So if you have a number in front of your exponential expression, you need to get rid of that first. So here I have y equals 2 to the x. My base is 2, and I want to write it in logarithmic form. So using this definition, that's going to be x log base 2 of y. Um, Here I do have a coefficient in front of the exponential 2 to the x, so the coefficient is 3. So the first thing I did was divide both sides by 3, and then I can rewrite it as x equals log base 2 of y over 3. And here are a couple more examples. Y equals 5 to the x. That gets rewritten as x equals log base 5 of y. And here, y equals 7 to the negative x. That gets rewritten as negative x equals log base 7 of y. And then so that's rewriting it in logarithmic form. You could definitely solve for x by just dividing both sides by -1. Or your other choice is to rewrite this as y equals 1/7 to the x. Remember, negative exponents mean that you can take the reciprocal of the base and then the exponent changes to positive. And when I do that, I get x equals log base 1 over 7 of y. So these two are equivalent, just written in different ways. Okay, so in these next few examples, we're going to go in the other direction. I'll give you a logarithmic expression or equation, and we want to write it as an exponential equation. So in number 3, I have log base 3 of 9 equals x. Using this definition up here, that is now written in exponential form as 3 to the x equals 9. So we were just being asked to convert. We're not being asked to solve for the variable, although we will be doing that in the future. Here I have negative log base 5 of x equals 2. It's the same rule as with exponents. You can't have a coefficient other than 1 in front of your logarithm before you convert it to exponential form. So if you divide both sides by -1, this is what you should be converting. Log base 5 of x equals -2, which is rewritten as 5 to the -2 equals x. So the little base in the logarithm is the base, the big number or expression in the exponential. Okay. Like I mentioned a minute ago, logarithmic equations can be solved as well as exponential equations. So we will have a whole section on solving these types of equations, but here's a little taste of it. So I have log base of 16 of 1/4 equals x. So in order to solve this, it is easier to solve this when it's in exponential form. So I have 16 to the x equals 1/4, and I get x is -2. Now, why is that? So if you know your rules for exponents really well, you might be able to come with that without running without doing too much work. But I know that 16 is the same as 4 to the second power raised to the x. And I know that 1/4 is the same as 4 to the -1. So here I can multiply the exponents, so I get 4 to the 2x equals 4 to the -1. And so that means, since the bases are the same, that means that then 2x must equal -1. And so x is -1/2. And remember, if I were to check this, put the -1/2 into the original equation, does that equal to 1/4? 6 to the -1/2 is the same as 1 over the square root of 16, and that is definitely equal to 1/4. So you could always check. You need to remember your rules for exponents and your rules for rewriting a rational exponent as a radical in order to do that. Number 6, example 6. I have log base 8 of n plus 1 equals 3. We need to solve for n. So again, I'm rewriting it as an exponential equation. So I have 8 to the third equals n plus 1. 8 to the third is 512. And then to solve this equation, we subtract 1 from both sides. So your n is equal to 511. Number 7, I have log base 7 of y equals -2. Again, I need to solve for y. So rewriting this in exponential form, this will be y equals 7 to the -2. Remember, negative exponents means you take the reciprocal of the base and then we'll square it. So your y is equal to 1 over 49. Okay, so now we're going to graph logarithmic functions, just like we did with exponential functions, and they do have something in common. So the graph of a logarithmic function has these properties. It has a domain that is all positive numbers, and the range will be all real numbers. The negative y-axis will be an asymptote, and because it's the y-axis, that's considered to be a vertical asymptote. We can also state that as the line x equal to 0. If your values of x are between 0 and 1, whoops, I think I moved something by mistake. If the values of x are between 0 and 1, then log base b of x is going to be a negative number, and you'll see that in the graph. When x equals 1, log base b of x will equal 0. And that's because, again, rewriting this in exponential form, b to the 0 equals 1. And when x is greater than 1, your logarithmic function will be positive. So that's why my range is all real numbers. I'm going to get some negative results, 0, and positive results for your logarithm. If the base is greater than 1, remember the base has to be positive. If the base is greater than 1, the logarithmic function will be an increasing function. If your base is between 0 and 1, it will be a decreasing function. So remember, we also had a difference in the behavior when we were graphing the exponential functions discussed in the previous 2 sections. All right, so to graph a logarithmic function, again, the easiest way to do this until you have a better sense of what they look like is to rewrite the logarithm as an exponential equation. And so this is rewritten as x equals 4 to the y. So typically we would be picking values of x and solving for y, but this time we're going to pick values of y and solve for x. So I'm going to plug in the y in here and figure out what my x's are. Because my range is all real numbers, y could be negative, positive, or 0, and I did a few of each. So here I have -2. When y is -2, x is 1 over 16. When x is -1, when y is -1, x is 1/4. When y is 0, x is 1, and this will be my x-intercept. When y is 1, x is 4. When x is 2, y is 16. So it's a little untraditional. We plugged in the y's we solved for x, but you still graph in the same way. This is the 0.116 negative 2. That means you move 1/16 units to the right and 2 units down. And so that's that point right there. 1/16 is pretty close to 0. Then 1/4 negative 1 is a little bit further to the right and up. 1, 0, my x-intercept is right here. 4, 1, and I didn't plot 16, 2, because I didn't have enough room on this graph. But you would just go 16 units to the right and 2 up. So you can see that your graph is increasing from left to right because my base was greater than 1. The domain is all positive numbers. You can see all of my x's are positive. My range is all real numbers. It's increasing over the domain. The x-intercept is at 1, 0, and I have a vertical asymptote right here on the negative y-axis, which is the line x equal to 0. Okay, so it's not the same shape as an exponential, but it is very similar. So later on, I'll graph an exponential function and a logarithmic function on the same grid. Okay, here we want to graph y equals 3 log base 2 of x. Here again, I have a coefficient, and I need to get rid of that coefficient first by dividing both sides by 3. And then when I rewrite this, it'll be x equals 2 to the y over 3. Just like the last example, I'm going to pick values of y, some negative, 0, and some positive, and plug it in, and then solve for x. So I picked values that would simplify nicely with the y over 3. So I picked negative 3, 0, 3, and 6, so that I'm only dealing with integers in my exponent. So when I plug in negative 3, here's the work, I end up with 2 to the negative 1, which is a half. So that is my first coordinate, 1/2 negative 3. When you plug in 0, you'll get 1. Again, that's your x-intercept. When I plug in 3, you'll just get 2 to the first power. That's 2. When you plug in 6, you'll get 2 to the second power, and that is equal to 4. So all of those points are plotted here. Again, this is increasing from left to right because my base is greater than 1. Domain is the same as the last example, all positive numbers, range is all real numbers. I have the same x-intercept at 1, 0. It's increasing over the domain from 0 to infinity. And again, the negative y-axis or the line x equal to 0 is your vertical asymptote. So it has exactly the same attributes as the last example. It just grows a lot faster. Like your y's get bigger a lot faster than in the last example. So here we have the log base 2 of x and transformations of it. So log base 2 of x is here in blue. And when you put a negative in front, remember that is a reflection across the x-axis. So that's the graph g of x here in red. So it is reflecting the blue graph over the x-axis. So the same behavior that was explained with polynomials and rational functions and radicals still applies to logarithmic as well as exponentials. And here, the graph of log base 2 of x is in blue on the right, but in this case, I have a negative in front of the x, and so that reflects it across the y-axis. So the reflection across the y-axis is the one h of x here in red. Once I reflect it across the y-axis, the domain of this one changes completely because then the domain will be from negative infinity to 0 instead of this one, which is 0 to infinity. For these, the domain is the same. It's just positive numbers. Okay, we have something called a common logarithm, and those are special logarithms that have a base of 10. With a common logarithm, you don't need to write the 10 here as a subscript. You don't need to write log base 10 of x, although it is possible that you might see that. When you don't see a number in this corner here, it means that it is a base of 10, and that's called a common logarithm. If you look at a calculator, you should have an log key that refers to a common logarithm. In fact, your calculator only has two logarithms, uh, a common logarithm and something called a natural logarithm, which I'll talk about more later in this lesson. And a natural logarithm has a base of the number e. So those are the only ones that are in your calculator. Any other logarithm of base 2, 3, 4, 5, 6, etc. Does not exist. So this can be done without a calculator, just remembering the relationship. It says to evaluate log of 1,000. So if you remember what that means in terms of an exponent, that means 10 to some power is equal to 1,000. And our answer is whatever this exponent is. The answer for a logarithm is going to be your exponent. And so what number raised to the third power will give me 1,000? That's going to be 3. So the log base 10 of 1,000, or 10 to the third, is equal to 3. So remember, the answer of a logarithmic expression is the exponent that would be associated with the base. The next one is similar. This is log of 1 over 100. I can rewrite the 1 over 100 as 10 to the negative 2. And so 10 to the negative 2 is equal to 1 over 100. So my answer is negative 2. If you plug this into a calculator, either part A or B, using the log function, that's your common log, it should give you the same answers. Here we do need a calculator because I cannot rewrite this number with a base of 10 the way I did here. 1,000 is 10 to the third, 1 over 100 is 10 to the negative 2. I really wouldn't be able to do that for 0.0640. So again, using the common log key and rounding to 3 decimal places, you would get that the logarithm is equal to negative 1.194. Here we have an equation with a logarithm, and we need to solve for the variable r. Okay, so in order to do that, we're going to have to rewrite this as an exponential and try to get r alone on one side of the equation. So the first thing I did was divide it by negative a so that the coefficient in front of the logarithm is 1. So I have negative c over a equals log base 10 of b over r. Remember, that means it's a common log, so you really don't have to write that 10 there. And so when I rewrite that as an exponential, that is 10 to the negative c over a equals b over r. Remember, that's what we're solving for. So what I did on the next step is I wrote this without the negative exponent. It's 1 over 10 to the c over a. And then if you cross multiply, the r gets multiplied by 1. The 10 to the c over a gets multiplied by b. So r is equal to b times 10 to the c over a. So that one doesn't really have any numbers. It's just practicing how to solve an equation and rewriting a logarithmic expression as a exponential. Okay, we have a new term here called the anti-logarithm. So if you are given the log of n, this means common log, base 10, then we call n the anti-logarithm. The expression that you're taking the log of is called the anti-logarithm. And because there is a relationship with 10, the base 10, you can solve for the anti-logarithm by using the 10 to the x key. So, and in some calculators, it might be called the inverse log key, and it'll make sense soon why it's called the inverse log. So this or this might exist in your calculator. So suppose I wanted to find the anti-logarithm of log of n equal to 0.929. So that means that 10 to this power must equal n. So that's why we use this key. 10 to the 0.929 gives me my anti-logarithm n. This is the value of n, 8.429. And again, I rounded here to the thousands place. Make sure that whatever the directions are, when you're doing a problem like this, that you round to the appropriate place. Here we want to find the anti-logarithm log of n equal to negative 6.9788. We use the same key, 10 to the negative 6.9788. And your calculator might give you something that looks something like this, but most likely it would look more like this, kind of something strange that maybe you've never seen before. So in order to rewrite it like this, is we're using scientific notation. And so I just went out 3 decimal places, so I only included this. And this negative 7 here means that's the exponent associated with 10. So this is 1.050 times 10 to the negative 7. That means I would move my decimal place 7 places to the left to get what the actual answer here is, which means your anti-logarithm is a very small number. This one will be done similarly. Here I have 10 to the 8.82436. Calculator might give you something like this. And then if I use scientific notation, and again, it's optional if you want to, but sometimes when they're big numbers or really small numbers, it's more convenient to read it like that. If I move this 1, 2, 3, 4, 5, 6, 7, 8 places, I'll have a decimal here between the 2 sixes. So this is 6.67360. I rounded off right here, times 10 to the 8th. So again, anytime you're rounding, that is an approximate answer. So this is what the calculator would give you. This is scientific notation. So I mentioned earlier that 10 to the x could also be written as the inverse of the common log, and that's because we do have inverse functions between exponential and logarithmic functions. So inverse functions are functions whose graphs are mirror images of each other with respect to the line y equals x. So this is for all inverse functions. The domain of the function is the range of the inverse function, and the range of the original function is the domain of the inverse function. So now we're going to look at exponential and logarithmic functions because they are inverses of each other. So if you remember, the way you find an inverse is you switch the x's and y's, and then once I did that, I need to solve for y. And the way I solve this for y is to rewrite it as a logarithm. So this is going to be y equals log base b of x. So y equals b to the x and y equals to log base b of x are considered to be inverse functions of each other. And so every exponential function will have a corresponding logarithmic function as an inverse. So if I have a common log, then the inverse would be 10 to the x. So y equal to log of x and y equal to 10 to the x are inverses of each other. When you have the other logarithmic function that I said is in your calculator, that is a natural log. Natural log has a base of e. So y equal to ln of x equals y, and y equal to e to the x are inverses. This is an L. This is an ln, natural log. It's kind of, the letters are reversed from the way you say it. It is not an I, so please don't make that mistake. Okay, so graphs of two inverse functions. Remember, e to the x and ln of x are inverse functions of each other. So here, e to the x is the one in blue. It's above the x-axis. It's increasing from left to right. Ln of x is the one in red. It is also increasing from left to right. And here, the domain is just positive numbers, but range is all real numbers. And remember, this is the mirror, y equals x. If you reflect e to the x over the line y equals x, you will get ln of x and vice versa. So remember, one of the definitions for inverse functions is that if you have two inverse functions, if f and g are inverses, then the composite will equal x. So here's the composite. E to the ln of x will equal x. Here's the other order. Ln of e to the x will also equal x. So that's really helpful for when you need to simplify exponential and logarithmic expressions. So remember, just to remind you why we have inverse functions, both exponential functions like e to the x and logarithmic functions like ln of x are one-to-one. When you have a one-to-one function, they will have a corresponding inverse. The domain for your exponential is all real numbers. The range is all positive numbers. The domain for ln of x is all positive numbers. The range is all real numbers. Remember, domain and range switch between two inverses. So the domain of e to the x is the range of ln of x, and the range of e to the x is the domain of ln of x. And that will be true for any inverse functions. Okay, since y equals b to the x and y equals log b base b of x are inverse functions, then this relationship of their composite being equal to x will be true no matter what the base is. What I did up here was when the base was e, but it would be true for any logarithm and exponential with the same base. So we're going to use that information to evaluate the following. We have to evaluate 5 to the log base 5 of 8. So that's basically what you're seeing here, except my b is 5. And so your answer is just 8, right? So just like here, the answer was x. Here, the answer is 8. E to the ln of 20, that's basically the same as this format, except my base is e, and so my answer is 20. Part C, ln of e to the 3, that's this example. Natural log has a base of e to the third has a base of e. They have the same base, so my answer is just 3. Right? It's just the exponent here. And log base 6 of 1 over 36, well, it is like this one, except I have to rewrite the 1 over 36 as 6 to the negative 2. So now these two bases are the same. My answer is negative 2. Okay, so this should be memorized and understood so that you can apply it. So here we want to describe the transformation of f of x equal to ln of x in each of the following. So we're going back to material that was discussed in chapter 2. So g of x is equal to the natural log of x plus 2 plus 5. This is going to be a horizontal shift 2 units to the left and a vertical shift 5 units up from the original function. Ln of negative x minus 3. This part is a reflection across the y-axis, and this is a vertical shift down 3 units. Okay, so you try, simplify each of the following, and so you're using a lot of the things that I already discussed. There are 8 problems for that, so give that a try. Good luck.